So we have the mean monthly temperatures in Raleigh in list 1. Our first question. The mean of Raleigh's monthly temperatures is 59.25 degrees Fahrenheit. Nice, they've done that for us. If you wanted to, how could you find the mean quickly with the calculator? Stat, calc, 1. Okay, so no 1 var stats. It's very helpful. There you go, 59.25 degrees. It's the first entry. Also note it gives you the sum, 711, and look at the bottom of the table. That matches up as well, 711. Okay, they want us to complete the 2 missing entries for March and July and the deviation from mean row below. So what you're going to notice here is that we are going to be working with how far each datum deviates from the set's mean. And it will give us an average measure of variability in the data set. Both mean absolute deviation and standard deviation use the deviation from the mean. For example, take a look at January, which has a temperature of 39 degrees on average. It deviates from the mean by negative 20.25 if you adopt the convention value minus the mean. Or symbolically, x minus x bar. Get used to these symbols. X bar is the mean of x. Okay, so 39 minus 59.25 is negative 20.25. That's how they're getting that. Okay, so find what it would be for March and for July. Ethan, what is it for March, please? Negative 9.25, thank you. And Maria, what is it for July? 18.75, thank you. Any questions so far? Now we are asked to add those deviations and then calculate their sum. Let's do this with technology, shall we? That's why we built these things, to make our lives easier, to do work for us. Soon the robots will be doing everything. I'm not sure what we'll be doing. So check this out. Stat, edit, please go to the very top of L2. We're going to use a list operation, an iterative operation here. So please press second 1. That will get you L1. And then do minus 59.25. I want to recreate the column that says deviation from the mean using my calculator. Okay, L1 minus 59.25. Enter. Sweet, right? All your deviations from the mean. Mara Pattison, ladies and gentlemen. When your calculator is not working, blame the user. Okay? You must enter the operation at the very top, like where the heading is. Okay. We good? You have noticed that our friend 1 var stats gives you the sum of a list. So let's use that to get the sum. Stat, calc, 1. This time specify L2. And then calculate, my favorite drink to get at Starbucks. What's the sum? 0. Okay, sigma x, capital sigma x, is the sum of x. It is 0. That's what it's supposed to be. That is the nature of the mean. The nature of the mean is such that if you add up all the deviations from it, including the signs, that sum will always be 0. If it's not 0, then something was in error. Okay? This is an issue. If it's always going to add up to 0, I cannot use this column to determine an average deviation from the mean. It will always be 0. So, look what they've done. They've taken the absolute value, which is the distance. Absolute value is distance. In other words, they just stripped the negative sign from those that are negative. So I don't think I need to ask you this question. I think it's very simple. March's absolute deviation from the mean is positive 9.25. July's absolute deviation from the mean is positive 18.75. Again, let's be lazy, or maybe more efficient is a more appropriate word for it. And let's have our calculator do this for us. Let's do this in L3. Does anyone know where the absolute value is, Laura? Math. Yes. So go to the very top of L3, then math, num, abs of steel, number 1. Now what? L2. Okay. The absolute value of L2, and then entree. There you go. So we're recreating the table. Now, as before, we'll do a good old stat calc 1. This time on L3. Say it out loud. What's the sum? Louder. 143. Thank you. Now we have something we can work with to find the average deviation from the mean. By the way, symbolically, this would be absolute value bar, x minus x bar, close absolute value bar. Okay, by the way, that was part C. I think you all know how to find an average. You take the sum and you divide by the number of values. That's what we're going to do next, to find the average deviation from the mean. So sigma, absolute value, x minus x bar, absolute value, all over n. This is what's called MAD, or AAD, mean absolute deviation, or average absolute deviation. We have the sum, it's 143. How many months are there in a year? 1,000, no, 12. So 143 over 12 is 11.9, approximately. Units? Degrees? Fahrenheit. What we just found is of much significance. This tells me that in Raleigh, the average deviation from the mean is about 12 degrees Fahrenheit. Okay. On average, the months deviate from the yearly average by about 12 degrees. Okay. This is a measure of variation. And it's a very useful one. Unfortunately, though, for reasons that I may get into later, it is not the most common standard deviation is. And there are calculus-based reasons and also personality-based reasons why standard deviation is used more than mean absolute deviation. Okay? Any questions, though, on MAD, mean absolute deviation? Okay. So you notice that if we left the negatives on there, the deviations from the mean always add up to 0. You can prove that to yourself with any set of data. So one remedy to that is to take the absolute value. That's how we get MAD or AAD. Another alternative is to square the numbers to get rid of the negative signs. That's what's going on in the final column, where it says squared deviation. Symbolically, this would be x minus x bar, that whole quantity squared. Again, let's use our calculator. We're getting some good practice here on using list operations. Hopefully you can figure this out by now. We can simply square L3. And that will get us the square deviations from the mean. So for March, it would be 85.56 about, or 563. That's the square of 9.25. And then for July, the square deviation is 351.56. That is the square of 18.75. As before, we will use StatCalc 1 to find the sum. We need that in order to get an average. So the sum of the square deviations from the mean is 2,208.25. Any questions on the first page? Okay, this is what standard deviation is going to use, the square deviations from the mean. So backside, please. As I mentioned, an alternative to working with absolute values is to square the deviations from the mean. We have already completed the missing entries in the squared deviations column of the table, and then we found the sum of those squared deviations. Letter F, divide the sum of squared deviations by 11, one less than the sample size. It's very natural to wonder why we're not dividing by 12. There are some instances in which you would divide by 12. If this was considered the population, you would divide by 12. Something that's interesting about standard deviation is that it is a biased estimate of a population standard deviation unless you divide by one less than the sample size. Not something that we're going to get into here, but just so you know. Okay. So, again, our sum is 2,208.25, and we're dividing that by 11. $200.75. Units? Degrees Fahrenheit squared. Because we square the deviations from the mean. This, my friends, is something called the variance, or the sample variance. When you divide by one less than the sample size, it's called the sample variance or the sample standard deviation. The variance is the square of the standard deviation. Okay. We don't want something that's in degrees Fahrenheit squared. So to unsquare it, we will use the inverse operation of squaring, which I think you know, the square root. 14.2 approximately. This is the standard deviation, or the sample standard deviation. This is the most common measure of variability in the world, at least in my experience. It shows up in many statistical formulas that you'll see later in the course. And when people are wondering how much variability exists in a data set, they usually go right to standard deviation. It's still an average. It's just not an arithmetic mean. There are different types of averages. There's the arithmetic mean, the geometric mean, the harmonic mean. This is something called a root mean square averaging technique. Root because of the square root. Mean because you take the sum and divide it by the number of, or something that's close to that. And then square because you are squaring something. RMS. If any of you study electrical engineering, as I did, you will learn about RMS. Because there's something called RMS voltage. Okay. Root mean square averaging tends to produce, or maybe always produces, values that are larger than regular averaging. So notice that the standard deviation is larger than the mean absolute deviation. That's to be expected. Does anyone know why that's happening? Yes. Why do you think the standard deviation is larger than the mean absolute deviation? Yes.
The mean absolute deviation is divided by 12, in this case, while in the standard deviation is divided by 1.
Okay. In the standard deviation, we are dividing by 11, whereas in the mean absolute deviation, we're dividing by 12. That is a factor. However, I don't think that is the larger factor. What do you think is the bigger reason why standard deviation is larger than mean absolute deviation? Think about how it's calculated. Matt.
Dividing the sum of the square deviation to the total.
Exactly. Exactly. You're dividing the sum of the square deviations, not just the absolute deviations. And I think you know what happens when you square numbers. They get bigger, and they get disproportionately bigger. Okay? So all it would take would be one value that's far away from the mean, and that is going to be a very large square. Okay? Good. Letter H. Use technology to verify your calculation of the standard deviation of Raleigh monthly temperatures. Then use technology to calculate the standard deviation of the San Francisco monthly temperatures. We can do that if we have time. I think we will. I have told you this already, but just to remind you that our friend 1var stats, we're going to do it on L1, gives you standard deviation. So do a 1var stats on L1. S sub x is the sample standard deviation. Notice it's exactly what we got, 14.2 approximately. And then lowercase Greek s, or lowercase sigma s, x, is the population standard deviation. This is the figure you would use if the data is considered the population. This one divides by n, which makes more sense when you're averaging to divide by n, not n minus 1. But this is a biased estimator of the true standard deviation if your data is considered to be a random sample from a population. Almost always we will use this one. And we're going to make an assumption here that if somebody asks for standard deviation, that we're going to give them the sample standard deviation, okay, S sub x. Nice, verified. Okay? Any questions on standard deviation, what it means, how it's calculated? What's most important is that you understand what it means, especially in this day and age. The computers do all the calculations for you. They make the graphs for you. Your job as the human being is to interpret. So it's much more important that you know what standard deviation means than can you calculate it by hand. All right? Let's take a look at San Fran. And let me see if I can relatively quickly pull that up. Ta-da! Sometimes I'm organized. All right. I'm just going to go ahead and clear L1 and then put San Fran in. 49 degrees in January, 52 degrees in February, 53 degrees in March, 56 degrees in April, 58 degrees in May, 62 degrees in June, 63 degrees in July, 64 degrees in August, 65 degrees in September, 61 degrees in October, 55 degrees in November, and 49 degrees in December. Before I do anything, should the standard deviation be more or less? It's San Francisco versus Raleigh. What do you mean you don't know? It should be less. Okay? Stat Calc 1. Tell me, what's the standard deviation? There you go. Good. This is what we expect. Because San Francisco has a lot less variability in its monthly average temps than Raleigh. So even though this is not an arithmetic mean, you can still think of it as a mean. You can think that on average, temperatures in San Francisco deviate about 6 degrees from their mean. Whereas in Raleigh, about 14 degrees. But keep in mind, this is not an arithmetic mean. There's part of me that would like that mean absolute deviation was more common than standard deviation, because I think it makes more sense to people. But alas, I wasn't born early enough. I would have had to have been born in the 19th century to have had a role to play there. Okay? Any questions on that activity?